Welcome to today's lecture. Today we will be computing some sample statistics for a quantitative variable. What we'll do today actually is just compute some of the more common numerical summaries. We start with a set of sample data, this 48233. That could be, for example, the number of people in line at the grocery store. So what we want to do is just compute a few basic summaries of that. Of course, with 5 numbers you really wouldn't need to do that much, so we'll compute the median, the mean, the variance, and the standard deviation. Those first two measures, the median and the mean, we'll look at where the center of the data are at. The second two, the variance and the standard deviation, actually they're pretty close to the same thing, as you'll see, one minor difference, but they measure how spread out the data are. Here's the numbers that we had, the 4, 8, 2, 3, and 3. To compute the median, just put those numbers in order, ascending order, so 2, 3, 3, 4, 8. And then just pick the number in the middle. For an odd number, I'll show you later what to do with an even number. It's pretty close to the same thing. Anyway, just put the numbers in order and then select the number in the middle of that ordered array. Okay, so when should the median be used? By now maybe you've read enough to know that there are 3 measures of central tendency, or at least 3 that are more commonly used than others: the mean, the median, and the mode. The mean is by far the most frequently used, but there are times when the median is a more appropriate measure. So let's take a look here. When data are highly skewed, or when there are outliers or extreme values, you should use the median. Now for right now, don't worry too much about the distinction between outliers and extreme values. That will become clear a little bit later in the class, and that will become an issue of some importance. But for right now, just when you have highly skewed data or when there are unusual values. So here's a data set, 2, 4, 5, 6, and 7. And if you compute the median number in the middle is 5, and if you computed the mean, we'll compute the mean in just a minute and a couple of other slides, but it's just what you normally think of as average. Add them up and divide by the number of them. You can see those are pretty close together, and they would both give you a pretty good idea of where the center, or what an average value would be in the data set. Well, let's look at another data set, 2, 4, 5, 6, and 70. Well, in this case, the median is still 5, but the mean is overly influenced by the value of 70, and so we get a mean, and you add those up and divide by the number of them, of 17.4, and that really isn't indicative of anyone in the data set, and certainly not like the majority of people in the data set. So the median is said to be resistant to the effect of skew, outliers, and extreme values. One instance of where you ought to use the median, which you're probably familiar with, is in the reporting of income. And the reason you want to use the median there is sometimes you have in your sample 1 or 2 or a handful of people who have very high incomes. And including those in your calculations would really change what you report as the center of the distribution in a way that makes it not very descriptive of most people in the sample, or the population for that matter. So for example, if you consider Benton County, if your sample happens to include anybody with the last name of Walton, then if you compute the mean, you're going to report the average income as being maybe in 6 figures. And that's certainly not true of the vast majority of people that live in Benton County. So in a situation like that, where you're going to have, in this case, some very extreme values, you really should use the median instead of the mean if you want to accurately describe most people in the sample or population. To compute the mean, we just add the numbers up. So 4 plus 8 plus 2 plus 3 is 20. And then we'll divide the sum of those numbers by the sample size. The sample size n is just the number of numbers in the sample set, and data set has 5 values. So to read through here, x bar, that's the symbol for the sample mean, equals the sum of the x sub i's. The x sub I is just whatever your random variable is. In this case, the number of people in line. So the I means it's a random variable, so just add them up for all 5 values, divide by the 5, and you have 4. This is usually what people think of when they use the word average, although technically speaking, average would also include median and some other measures that you could use to look at the center of a distribution. Next, we're going to compute the sample variance, and you can see I have the formula up here. S squared is the sample variance, and then we're going to add up what's called the sum of the squared deviations. The center of that part, the x of I minus x bar, that just means we're going to subtract the mean from each value in our data set. Then we're going to square each of those values and add them up. The numerator in this expression is sometimes referred to as the sum of squared deviations. More about that in a later lecture, what that name means. And then divide by n minus 1. Like, it's not exactly this, but something like the average squared distance from the mean. Well, anyway, just going through this numerically, we're going to first compute the deviations. That's subtracting the mean from every point. So the sample mean was 4, so 4 minus 4 is 0, 8 minus 4 is 4, and so on. You should note, and this will always be the case, that this column, which we can refer to as deviations, deviation or difference of each value from the mean, will always sum to 0. Next step is to square each of those deviations. We want to get something like the average of the deviations in the n. Well, we can't average the deviations because the sum's always 0. So we square in order to get all positive numbers. At least that's one reason to do it. There's some other advantageous reasons that will become evident later in the class. But anyway, square each of those. 0 squared is 0, 4 squared is 16, minus 2 squared is 4, and so on. Then add those up. So I have the sum of the squared deviations. That's the numerator of the expression above. That is the sum of the x of I minus x bar squared. So then I just need to divide that by n minus 1, and I have my variance. Again, that's the sample variance, s squared. You may want to keep in mind, that this is the sample statistic. This comes from the data. It's not a characteristic of the population itself. So to compute the sample standard deviation, we basically just do all the steps that we did for the variance, but now take the square root. So the standard deviation, s, is the square root of the sample variance, s squared. So the interior of this formula, everything under the radical, is exactly the formula we just had. So all we have to do is make those computations and then take the square root. The big advantage of the standard deviation is it will be in the same units as our original data. So the variance, when we ended up with that 5.5, if you want to put units on it, 5.5 people in the line squared, which really doesn't make any sense in a conversation, that's for sure. So anyway, we take the square root of that, and we'll have approximately 2.35. Well, since we've got the calculation out of the way, let's just take a little bit closer look at what it means to have a mean and a standard deviation. Looking at our central figure for the class, the sample mean is collected from the data or from the sample. We use that to estimate the population parameter mu. This is the true mean of the entire population. Usually don't know what it is, so even though there is a formula to calculate it, we really don't use that formula because we don't have, at least we very seldom have, access to the whole population and the data from that population. Keep in mind here, x bar is the sample statistic. It's collected from the sample data. Mu is the population mean, and that's what we'd like to estimate. Okay, the sample standard deviation, and the sample variance as well, but we're going to focus on the sample standard deviation for a while, is also collected from the sample data, so it's a statistic, and we're going to use that statistic, the sample standard deviation, as an estimate of the variability or the population standard deviation for the whole population again. Another thing I want to do here is just take another look, a graphical look at what mean and particularly what standard deviation means. So in this set of data here, I just have a couple of histograms, graphs of the variable, and what you can see is that the means of the two samples are roughly the same, 175 and 176. They're not exactly the same, but if you look at the distribution of data, they're really both pretty close to the same. But if you also look at the data, and I have these on the exact same scale, you will note that the distribution on the left is quite a bit narrower than the distribution on the right. So the standard deviation on the left is smaller. This data has less variation. It's less spread out than the data are on the right-hand side. You can see that I've designated that with the arrows at the bottom, and you can see that on the right has a higher variability and a higher standard deviation than the graph on the left. Okay, here's a website, and I have links to this on my website as well, but let's just go take a look at it. Practice matching histograms to means and standard deviations. So looking at these, note down at the bottom we have means of 11.6, 13.6, 10, and 4.3. So it's going to be pretty easy to drag that on over here. You can see at the bottom it's indicated true that I have in fact found the right mean and standard deviation there. Of the remaining three, one of them has quite a bit larger standard deviation, and I'm going to drag that over here. It's a little more spread out than the other two. The mean's also higher, but I'm really looking at the spread here. And the other two, means of 10 and 11.6, well, you can look at the means, but also just look at the variability. Even though there's not a huge difference in the standard deviations, 1.1 and 1.4, this one I believe is clearly narrower, less spread out than the first. And you can see this has both a higher mean and a slightly higher standard deviation as well. So I'm going to load another set of here just to get a little bit more practice. Well, I'm just going to start off with, I have two of these on the bookends here on either end that have quite high standard deviations. The data are spread out. I have one with a mean of 13.8 that's pretty spread out. That's a high standard deviation of 4.5. And one with 9.9. Well, it looks to me like this one's going to be the 9.9. There's a little bit of data on both sides of 10. This one has a higher mean. You can see it's a little spread out, but most of the data are on the high end there. And on the other two, you can look at the means, or you can just look at the standard deviations. This has the lower mean, and this has the higher mean. And you can see with this one also has the lower standard deviation. They're a little more scrunched together, more narrow distribution than this one. Range of 11.4 and 10, but one of them, and then let me go on here, and we have 6.2 and 5.3, which is going to be these two, but the standard deviations are quite different from one another. So this has a mean, or 10 or 11 or so on, and large spread. Same general area on the mean, but small spread. And on this one, and this one has a relatively large spread, so I'll put the standard deviation of 3 there. And this one has a relatively small spread, so I'll put the 1.2 right there. Anyway, I recommend that you go to this website and try this a little bit on your own and make sure you can do those right.